If AI can generate photorealistic images like this on the screen, why does it struggle to keep the same face for just a few seconds in a video? Why do characters suddenly change appearance, clothes morph, and backgrounds differ over time? The answer lies in one of the hardest problems in AI video generation, temporal consistency. And today, we are going to see exactly why this happens and how modern AI models are trying to fix it. Let's start with the core issue. When humans watch a video, we instantly understand that every frame represents the same world evolving through time. AI doesn't naturally understand that. Many image generation systems were originally designed to create a single image. When we ask them to generate a video, they suddenly need to create hundreds of images that all agree with each other. If that agreement breaks down, we get identity drift, clothes changes, and shifting backgrounds. That's exactly what we are seeing here. To understand why video breaks, we first need to understand how modern image generation works. Most AI image generators use something called a diffusion model. The process begins with pure random noise. Nothing meaningful exists in the image yet. The model then repeatedly moves noise step by step. At first, rough shapes emerge, then edges become visible, then recognizable objects begin to appear. Eventually, a fully detailed image is generated. The equation shown here represents a single denoising step. This process can be repeated hundreds or even thousands of times before producing the final image. For a single image, that's manageable. For video, things become much harder. Let's compare image generation and video generation. For an image, the model performs one complete denoising process. That's it. For a 5-second video at 24 frames per second, we need around 120 frames. If each frame requires roughly 1000 denoising steps, that's approximately 120,000 denoising operations. But computation isn't the real problem. The real challenge is consistency. Every frame must agree with every other frame. The same character must remain the same character. The same shirt must remain the same shirt. The same environment must remain the same environment. And that's where AI starts struggling. This slide shows the real challenge. Consistency isn't just required across space, it's also required across time. Within a frame, the pixels must form a coherent image. Across frames, those pixels must evolve consistently. Humans solve this naturally. We understand that a moving object remains the same object. AI models must learn that explicitly. They must learn that the face appearing in frame 1 is the same face appearing in frame 100. This requirement is known as space-time consistency, and it's one of the central problems in modern AI video generation. When temporal consistency isn't enforced, several failure modes appear. The first is identity loss. Facial features slowly change over time because the model isn't perfectly remembering previous frames. The second is motion drift. Objects stop following realistic trajectories and begin moving unnaturally. The third is frame mismatch. Adjacent frames disagree on colors, textures, lighting, and geometry. The scary part is that these errors compound. A tiny mistake in one frame can become a major artifact several seconds later. That's why longer videos are much harder to generate than shorter clips. One of the first solutions comes from classical computer vision. It's called optical flow. The goal of optical flow is to estimate how every pixel moves between consecutive frames. Imagine tracking every pixel in frame A and predicting where it appears in frame B. That's exactly what optical flow does. The equation shown here is called the optical flow constraint equation. Ix and Iy represent spatial image gradients. It represents change across time, and U and V represent pixel velocity. By solving this equation for millions of pixels, we obtain a motion field describing how the entire image is moving. Instead of asking the AI to guess motion, we explicitly tell it how things are moving. That dramatically improves stability. Here we can see the impact of optical flow. Without optical flow, The model generates frames with limited understanding of previous motion. Objects can jitter, characters can wrap, motion can become unstable. With optical flow, features from previous frames With optical flow, features from previous frames are projected forward using motion vectors. The model receives guidance about where pixels are expected to move. Think of it like giving the AI a roadmap. Instead of inventing motion from scratch, it follows trajectories already established in previous frames. That's why the motion appears much smoother and more natural. Optical flow helps with motion, but what about memory? What if a second character appeared several seconds ago? How does the model remember what they looked like? That's where temporal attention comes in. If you have watched my transformer videos, you'll know that attention helps model decide what information is important. Temporal attention extends this concept across time. Instead of only looking at the current frame, the model can actively reference earlier frames. Previous frames become memory. The current frame can retrieve information from the memory whenever it needs it. This significantly improves long range consistency. Let's go one level deeper. The current frame generates query vectors, previous frame generate key and value vectors. The model compares queries against keys to measure similarity. The resulting attention scores determine which previous information should influence the current frame. That's what this equation represents. The softmax function converts similarity scores into probability. These probabilities determine how much attention is paid to different regions of previous frames. In simple terms, every pixel can ask which previous frame contains information relevant to me. That's how the model builds temporal memory. And that's why modern video models can maintain consistency for much longer durations. Now let's look at a different approach. Instead of generating videos frame by frame, NERFs build an entire 3D world first. NERF stands for Neural Radiance Field. A neural network learns a continuous representation of a scene. Given a position in 3D space and a viewing direction, the network predicts density and color. Density tells us whether something exists there. Color tells us what it looks like. Once that 3D world exists, we can move a virtual camera through it and render new views. Instead of generating independent frames, we are rendering different perspective of the same world. This is why NERFs are so powerful. The source of consistency becomes the 3D scene itself. The same character exists in the same location. The same object exists in the same location. Different frames are simply different viewpoints of the shared world. Identity drift becomes much harder. Geometry remains consistent. Lighting remains coherent. Instead of forcing consistency after generation, NERFs build consistency directly into the scene representation. Today's best AI models combine multiple solutions. There isn't one magic technique. Diffusion models provide image quality, optical flow provides motion guidance, temporal attention provides memory, 3D representations provide geometric consistency. Modern systems like Sora, Veo, Runway, and Luma combine these ideas into unified architectures. The entire industry is moving toward a new perspective. Video is no longer treated as a sequence of images. It's treated as a single space-time problem. And that shift is driving the incredible progress we are seeing today. Temporal consistency is improving rapidly. Today's systems can generate short clips with increasingly stable characters and environments. Future systems will maintain consistency for minutes instead of seconds. We'll see controllable actors, editable scenes, persistent characters, and eventually fully AI generated films with cinematic level coherence. The biggest obstacle has never been image quality, it's been consistency. And we are getting closer to solving it. So the next time you see an AI video morph unexpectedly, remember what's happening behind the scene. The model isn't just generating one image; it's trying to generate hundreds of images that all agree with one another across both space and time. And that's one of the hardest challenge in video generation. Technologies like optical flow, temporal attention, and NERFs are helping solve that challenge and pushing AI video closer to true visual understanding. If you enjoyed this deep dive, make sure to like the video and subscribe for more content on AI, ML, neural networks, and how these systems actually work under the hood. Thanks for watching, and I'll see you in the next one.